Thank you all for coming virtually out to the PyData DC Meetup. Today we'll have Layne talking about reproducible rapid deep learning. He's lead community developer with AIQC. So before we get started, just want to make sure that we're having an open, conversation with, accepting people of all different experience levels. So, people, as you have questions, feel free to send them in via chat or other channels that work best for Layne, and we'll be happy to help there. Going to open up us as we get the PowerPoint moving. There we go. So I'd like to also thank our sponsors, MetroStar, Spell, NumFocus, NVIDIA, and Capital One for making PyData possible. I believe we have some announcements, so I'd like to open up the channel now for anybody that has any announcements to make.
Hey, can I make a job announcement while we're waiting to see if Hussein's around?
Yeah, sure. Good to see you, Paulo.
Hi, everybody. I have some friends in Nashville. They're looking to hire some data scientists, so I'm going to post the links to the jobs in the chat. That's all.
Awesome, thanks, Paulo. And we've also got some positions open here with MetroStar in the data science team. So we'll also post those positions in the chat. Those include data scientist, senior DevSecOps engineer, and a lead AI evangelist. Sorry if I mispronounced that. But without further ado, I'm going to pass it off to Layne to get started.
All right, thanks so much for hosting, guys. I'm really excited to get this moving. So I'm going to go ahead and share screen. Hopefully it's the right one. And are you guys seeing a big black and gold logo? Thank you very much for the thumbs up. Appreciate that. So as you guys mentioned, today we'll be talking about rapid and reproducible deep learning through the framework of AIQC. And just as a brief agenda, we'll provide an overview of the framework. We'll jump into a live demo of it in action, and then we'll get more theoretical and talk about a lot of the pre-processing challenges that the framework sort of glosses over, and but they're really kind of embedded in a lot of machine learning workflows. So it's good to bring those to light, so you don't just see a high-level framework. And this is, a pretty casual setting, so feel free to interrupt and ask Q&A along the way. So the origin story of AIQC goes back to my most recent role as a product manager working with big pharma on large-scale national biobanks like UK Biobank and Genomics Medicine Ireland, where they're gathering anywhere from 100,000 to 500,000 whole genome DNA samples coupled with phenotypic data. And they have, entire teams processing the raw data from blood to bits, and statisticians and computational biologists interpreting that data and looking for drivers of rare disease. And to my dismay, I kept waiting for someone to bust out the dino DNA, but it never really happened for me. And similarly, I kept waiting for someone to say, like, all right, now is when we start the machine learning. But that never happened. And I was pretty flummoxed as to why, right? State of the art is association studies. And when you're dealing with data that's this highly dimensional and biologically complex, I don't think that's really good enough. So I set out to uncover why this is happening, right? And at the end of the day, a lot of the scientists didn't really look like this, but this is the persona, right? You're dealing with people that may be PhDs, doctors, not necessarily the world's best or world-class programmers. As informatics emerges in each field, I think that'll start to change, but right now, they're fundamentally not programmers. And similarly, they're not data scientists, right? They're biologists. And when you consider the fact that machine learning workflows are kind of scattered across the internet in tutorials and cookbooks, they haven't really been centralized. They're in different frameworks right now, Keras and PyTorch and TensorFlow and more, right? This places a lot of stress on them because there's a lot of programming that has to happen to fill in the gaps when you're doing these different machine learning workflows. And there are, solutions out there. But they're really kind of in like SaaS walled gardens and expensive clouds. Most science and academic science research is being done on high performance HPCs, local, and they may not have the budgets to kind of tap into those resources, right? So that's kind of why machine learning isn't really being adopted, right? They could perhaps run some scripts, but not implement a workflow like this end to end, where they have to do the programming to piece together each step that you see here to pre-process your data and then apply a model on top of it and evaluate that model. So having stepped through most of these analyses and read through most of the textbooks that are out there on this stuff, I thought, well, can I automate this? Can I simplify the workflow into a high-level API that they would be able to use and feel comfortable with? And ideally, I'd like it to be reproducible, right? Because I was kind of conducting my own experiments I was SSH'd into some server and it wasn't necessarily reliable. And then when it came time to produce the plots and the metrics, I was like, this is just a mess. I want all of this kind of saved, and I don't want to have to ever retrain my models or lose them. And of course, it would be open and free. So we would really enable open science and push this kind of stuff forward. So the framework that we've built so far, and now I say we've got it's an open source community. It's growing right now. We're at about a core team of 5 developers, and we're looking to expand that a little bit. And each kind of developer is taking on a different slice of this. So on our x-axis, we have different data types. And the blue is what we support right now. So image-based data and tabular data, or just spreadsheets if you're not into data science. And then on the left are the different types of analyses that we support. So as you can see, our framework is ready for Keras and PyTorch for classification and quantification, for tabular and image, which is kind of like the bread and butter of deep learning. And we'll look to expand that over time. So the framework itself starts out with pre-processing, right? There are different types of data sets for the different types of data that we just saw. And then you can, with just a single variable, you can cross-fold your different data sets. And those are stratified, doesn't matter what D type they are, if they're continuous or not. And from there, you can apply preprocessors the same exact way. Like if you want to do encoding on a specific D type, but not another D type, and it doesn't really matter if that's 1D or 2D data, it knows how to handle that, and it knows how to piece together all of your preprocessing steps at the end of your pipeline object. So it's incredibly flexible, and it solves a lot of sources of bias that we'll talk about after the demo. Next is the queued tuning, just experiment tracking. It's really just the functions that no one wants to write. Some of the highlights here are that you can not only define hyperparameter values, you can treat your topology as a parameter. So if you want to say, like, I want this many blocks in my model, or I want to use this loss function here, it's pretty intuitive to do that. You just pass in a dictionary of Python variables as keyword arguments and into your functions, and it gives you pretty much unlimited flexibility with what you can do. That's going to queue up a queue of models to train, and then automatically every single model job is scored with metrics and charts that are specific to the type of analysis that you're conducting. So like regression has different plots and metrics than classification. And then as of this morning, you can apply the same pre-processing steps way back here to a brand new data set for inference, because everything is persisted. So it's really easy to just drop new data in there and get results. Of course, all of this is reproducible. There is a SQLite database file that gets set up when you just import the package basically, and every single kind of step that you see here is basically an object in a high-level API for machine learning. So you've got a data set, split set, feature set, fold set, algorithm, job, prediction, predictor, pretty much everything you would expect. And it's just a pip package that you can download and install. And let's take a look at what that looks like. So before we get into the demo, do we have any questions before I just keep kind of rambling on at the high level? And I'll just pause for a second. And okay, so let's jump into it. So this is an example where we're going to do just regression, nothing too fancy, on some data that's coming from the Kepler satellite. And what we want to do is predict the surface temperature of different exoplanets based on the data that's coming into the satellite. It's just tabular data. So I'm going to import my deep learning dependencies and my encoding dependencies and import the library. And this is all it takes. What it'll do is it's going to set up just a folder on your local desktop that's operating system agnostic, install that SQLite file, and make sure that you can connect to it successfully and create all the tables within it. Okay, and there's this datum module. There's some built-in data sets that you can play around with that are well suited to different types of analyses like regression and classification for image and tabular data, right? So here's what this data looks like here. So you can see we've got a whole bunch of float data, and one looks like a categorical, and look at that. And again, I'm not using the library right now. I'm just kind of exploring the data just to give you guys a sense of what it looks and feels like. And if we plot it, that'll take a second. But here's kind of what that looks like in 3D. You've got different planets of different temperatures that are different distances to the sun and densities and fun things like that, right? So it is fairly dimensional. Now, there's two objects in the high-level API. You've got this pipeline object, and then that's ultimately going to feed into an experiment. And these, pretty much each line or a few lines is an object within a lower level API that kind of connects its, so I don't want to get too much into this, but yeah, we've glossed over it and made it easy for you. So a split set is, train, test, and validation, right? And depending on how you set that up, you can say, this is the size of my validation split. We'll talk about why validation is important. And this is the size of my test split. I didn't specify cross-fold validation. If I wanted to, I could just say like fold count 5, and it would handle that for me. And then this is a stratification parameter for how many bins I want each split or fold to observe. The data itself is just that data frame that we talked about. I can force my own D types in ingestion because we're going to save this as a Parquet file behind the scenes so that we can access it on the fly, which is helpful for like time series data where you have to do a lot of normalization. And then I just say, this is my label column, and I want you to use all of my features. In the lower level API, you can get very specific about like what you want for labels and features. And then we get into encoding, right? And these are just, single lines. I think I introduced a feature where it'll just use the right defaults. So you don't wind up with sparse matrices that don't work in Keras. But anyways, you can specify several feature encoders sequentially with different filters that you want to apply to it. And it'll just concatenate your features back together when it's done encoding, and they'll be in the right order. And it's going to apply these encoders to each of the splits and or folds that you have specified, right? And this is just print out that, hey, we actually fit the data and it works. So you're good to go. You're not going to run into problems when you train your model. Although I did push some new features at 5 o'clock, so who knows? Then we get into the experiment object, right? So you have a model which is composed of features to build, train, predict, calculate loss, and optimize, right? And these work for both Keras and PyTorch and TensorFlow too, right? So what you can do, you can leave most of these none, and there are defaults. But if you want to get in here and customize some things, it's automatically going to pass in the shape of your data. So you don't have to worry, especially when you're working with image data, you don't have to do all those weird calculations, and it's going to give you a dictionary of hyperparameters that you specify. So you can do whatever you want. You can just pass in Booleans for batch normalization, and it'll allow you to toggle that on or off when it builds the actual, Python script of this function, right? So here you can see that we're tweaking the topology. If I want 1, 2, or 3 blocks of bad, batch normalization, activation, and dropout, I can just change a number right there. So I don't have to make a new model or experiment or anything. And let's see, for a simpler parameter, like I can change batch size if I want to, right? So let's make sure I've actually defined these functions, define the hyperparameters, and then specify the type of analysis that I'm conducting, a regression, which is going to have, it's going to expect like different encoders. It's going to inspect like different types of labels, like you can't run regression on a categorical label. And then I'm going to say, use this encoder set in case, you can just pick which pre-processes you've defined to actually use it. If I wanted to run each non-deterministic model 3 times, you can do that. But yeah, let's kick it off. I should have done that a while ago, so we don't have to wait. These are pretty small models on this pretty small data frame. It used to support background processing until Python 3.8. And that broke a lot of background processing stuff. So what you have here is you have a queue of models that's looping over all these different combinations that I've defined above, right? And what's going on is behind the scenes, when it's done training the model, it's calculating all the metrics, and it's generating all the data that it needs for the plots, so that I can very easily, when it's done running, interpret the results. So what we're going to see here is a data frame of the metrics for every single split. And this works for cross-fold validation too, right? So I don't have to do any of this by hand. So I see for the model that I trained for test validation and training splits, here are the metrics. And if I want to compare across models, let me zoom out a bit. This is kind of my favorite chart I made called the boomerang chart, which shows you, train, validation, and test metrics for each model. So you can, and these are interactive. So you can say like, oh, clearly like this model is better than the other one over here. And then you've got everything that you would expect, like access to learning curve data and the raw hyperparameters. And in classification, I'm just going to go ahead and try to kick off this entire notebook. It's a little bit more computationally intensive, but what it's doing is demonstrating how you can ingest brain image data, looking at both benign and malignant tumors, healthy, cancerous brains, and you can pass in a tabular label. Similarly, yeah, you can define your topology very flexibly, say what hyperparameters you want, and make an experiment. It's all the same pretty much workflow, but with different data types behind the scenes. And hopefully we'll trigger some early stopping here. But the point that so it broke 90%, so it's going to stop, and I'm just going to kill it. I'm going to interrupt it. And if I resumed this, it'll pick up right back where it left off, like on the next model that it needs to train. Because again, everything is saved, so it knows exactly where it is in the training process. So here's kind of that good model, and you can see it bonked on our test. So yeah, definitely overfit, 98% accuracy on the training data and tailing off on the other ones. But this is very easy to see now that you're calculating the metrics on each split, right? And then here are the classification charts, ROC, precision recall, and an interactive confusion matrix, which is our newest contributor submitted feature. So thank you for that. Now I'll jump back into how are we doing on time? We got like another 5 minutes or so.
Yeah, we're all set. You have more than 5 minutes.
Okay, great. Thank you. So some of the pre-processing problems that this solves, right? And I'm not going to read this slide to you because we'll talk through each example, but when you're evaluating data, when you're evaluating your models on your test split, like let's say this is pretty typical, your first run of the model, you train it and you are able to successfully learn, but your test score is still lagging far behind your training scores, right? Now, if you make changes based on this information over time, you can say, oh, like, yeah, when I did this, this increased, my test score increased. And then eventually you can push your way up to good accuracy on your test data set like this. But the problem is that when you're changing your parameters based on this direct train and test, you are effectively acting as a second model that is optimizing the hyperparameters based on how your model performs on the test data, which is supposed to be held out and separate, and you've never seen it before. But you're literally saying, here's how these hyperparameters do on data that I've never seen before, and then you're making changes based on that. So that introduces major bias, and that's why it's really important to use a validation split. I didn't show it, but there's a hide test parameter that you can set to true or false if you actually want to hide it. So you might do a bunch of training just on validation splits. When you feel like you've got something ready, you would flip it over and enable the test in your metrics, right? And if you want to solve this, a problem that I found was that validation splits aren't treated as equal. Everything is train test split, right? All the tutorials start like that. And if you want to do make your own validation split, you have to do algebra, and it's lame, right? Python's not about math, at least I don't think it should be. So another source of bias is leakage, right? So I mentioned, humans training models based on test data. This is about what happens when you encode your data not outside of your training set. So let's say this is cross-fold validation, right? And the gold is what you're actually training your model on. And the green is validation, the blue is test, right? You should only really be encoding your data based on the train, right? So you fit your encoder to the train, and then this should say transform, actually. So you transform your unseen data based on that. It's like someone telling you to guess how much, guess how many people are in a room, and you know how many, the average already. You know the average of how many people are in how many rooms. So you shouldn't be encoding your entire data set. You need to encode separately, and that's what one of the main things that AIQC does, and it works with cross-fold validation, which is tricky. Right. So. And then encoding itself is pretty much a nightmare. So this is, and I mean that in the best way possible. I love the scikit-learn tools. I'd be nowhere without them. This is built pretty much entirely on top of scikit-learn for pre-processing and Pillow for image data. But as I'm starting to learn myself, different contributors will think about schemas and how to structure their code differently. So each scikit-learn encoder doesn't even really belong to the same module when you look up from it. So on the right, on the x-axis is the data type, and then on the y-axis is the different encoders. And a 0 is if it works with that data type or dimensionality, and a 1 and 0 means it does or doesn't work. So there's a lot of trial and error. And when you're encoding programmatically, this can be a bit of a nightmare because you don't know what shape the data is and you don't know if it's going to actually work. So you have to write logic to handle that on the fly. And then finally, this is the last thing I'll bring up, is a lot of experiment trackers out there just kind of discard the data. They're only focused on the hyperparameters, and you could do that yourself. Just save your hyperparameters and model in a pickle object, right? And the main thing I see when I look at this now is instead of X and Y or whatever, I always mess it up, just features and labels. Let's treat these not as machine learning metadata. Let's treat them as well-defined constructs, because that's what they are. And when you do this, your pre-processing really only exists in memory. So if it wouldn't fly in a 6th grade science experiment, it shouldn't fly when you're trying to pass something through the FDA, right? When someone asks you, what data did you use to train on this? You're like, I don't know, like 2/3 of them, you know, that shouldn't fly. We need stronger data lineage for end-to-end and reproducible data science if we want machine learning to be taken seriously. So yeah, that's the end of my talk. And again, thank you so much for hosting me.
Well, thanks again, Layne, for the demonstration. It's awesome. And so anybody that wants to stick around, this is the part where we open it up for questions, as well as just really the opportunity to network. But first, I would love to open this up for anybody that has any questions for Layne on the AIQC demo we just went through.
While people kind of think about that, someone asked if it's on GitHub, and yes, it most assuredly is. So here is the GitHub page. There is a well built out documentation portal on Read the Docs that walks through all of the different types of analyses that are supported for both Keras and PyTorch, tabular and image data. And you can learn more about joining the community if you'd like to get involved.